recent, and this is first time in our deep learning course I'm going to cover, because in last 3 to 4 years when I was covering, I didn't have covered this particular topic. This is a brand new topic which is not being covered till in all of my previous offerings. And this is actually transformers. So today we are formally going to start transformer. Try to spend good amount of time. Let us see how much amount of time. But right now, if you read any, I mean, most of the recent new papers which are coming, they are going to see how they can apply these transformers and long formers and birds and self-attention, GPT, and so on. Huge amount of work is actually happening in this area. So we are trying to move into that. And before going to talk about that, we will have to really actually understand the thing that is anyways being covered previously, which is if I say recurrent neural networks. And transformers are actually a replacement, or one can say a better, efficient and performing alternative to recurrent neural networks. So before going to talk about that, we will have to somehow brush up our previous RNN things. So if you understand that if we are looking for recurrent neural networks, then what is the thing that you are having some, X1, X2, X3, X4, and so on. So there is actually a time series. There is a dependence which is being there, and temporal dependence is there. And you have a network piece over here. This is our neural network that we are acting, and given work like this, what you want is that if I see this, what is the output that I am going to generate? If I see this, then what type of output I'm going to generate this? And if I see this, then what type of output I'm going to generate this? And this output is not only being dependent upon this guy, it's actually being dependent what you have seen till now. And because of that, they actually become inherently sequential. If you wanted to talk about this, then you must have to see that what has happened till now. Then only you are able to somehow figure out that what is going to be the output for this. And this is actually the biggest bottleneck of any RNN network, that if you wanted to somehow predict what is this, you will have to predict intermediate things. If you don't do that, you will not be able to predict this. And that is the reason that even if you have 10 different cores, core 1 for this, core 2 for this computation, 3 and 4. So because GPUs are there in that, you're having so many different cores which are possible. But you cannot parallelize because it is inherently sequential. This thing is going to be, first of all, generating this, and then this thing is going to generate this. In fact, the way in which neural network is being trained, I am going to show, and then we will very easily understand that how these neural networks are actually being tested. So you show your X1. So your neural network is there. Only I am going to use the current input. I am also going to use the previous state of my network. Please mute your mic. Previous state of my network. And you have got your input, which is like this. Along with that, so this single thing is not going to determine what is going to be here. Along with that, I need to know that what was my previous state. So this thing and this is going to tell me what is the my current state, and depending upon my current state, I will somehow figure out this. So let us see that how it works. X1, so you have got this thing which is actually being unrolled, and this is your single recurrent unit that we already have seen in much great details. This is the initial state of my this neural or the recurrent unit, and then X1, and this is going to determine what is going to be my next state. And given this next state, given this next state, and given this next state, you are going to generate this thing. So now you can understand that if so suppose that you wanted to generate y3, then you take this x3 and you take your previous state. Both of these things are going to be used to give you the current or the A3 or the current state of my network, and then you generate. the next output. And then, and in this way, what you can see is that one important thing, by the way, is that your network is going to be fixed. That's why I have shown it as a shared weights, and they all are actually sharing the weights. In fact, this is only one single network to which initially you show this, then you show this, then you show this, and keep on doing the thing. The network remains to be the same with these set of parameters. That's why they are all being shared over here. And and given this network, these two things actually got converted into this thing, and this thing and this thing is actually got converted into this. And from this, or the current hidden state, how you can go to your next state is that you have another network which will take, and which is again being shared between all of the outputs. And that's actually that's going to take only the hidden state, and given this hidden state, it's going to generate the outputs for me. And once you've got your outputs for every state, you have got your output. For every time step, you have got your output. The corresponding loss is here, because you also know that what is your ground truth. So the distance between the predicted and the ground truth is going to tell you that what is the loss number 1, loss at state 2, loss at time step 3, and so on. So for all time steps, you compute the loss, and then you add the loss. This is your final loss, and then this is actually the way in which this got actually back propagated. And this, you all understand that this back propagation was actually in time. So this was actually the way in which this RNN networks actually works in great details. I assume that we have seen that how these things are actually being working. Is there any doubt? Is there anyone who wanted to say anything about this or having any doubt about it?
So may I ask,
Yes.
so like for any recurrent neural network, we say that the network has to remain same, by
Yeah.
which what we understand that the network parameters should remain same.
Yes.
Now, when is it that the network parameters get updated? Like if we pass one entire sentence, is the updatation after one entire sentence?
Yes, that is perfectly correct, and that was actually back propagation in time. Let me tell you this thing again. I require some space to write for. Okay. So what is a good place to write? Probably here I can write, and then I will rub it. Yeah, so what you have said is that suppose that I have sentences like this. This is sentence number 1, then the sentence number 2, then the sentence number 3, and sentence number 4, and keep on doing. And then I have, this is my final sentence. The sentence number 1, sentence number 2, and keep on doing, and this is my final sentence. And and what you are going to do is that within given in each sentence, you have got words. Your RNN is here. It keep on unrolling. It keep on unrolling until and unless one thing is that you show the whole thing to this. First you show this, then this, then this, then this, then this. Keep on unrolling. Keep on unrolling. And unroll and unroll and unroll, and wait when you are done with this. And at this point, when you are done, after showing the last thing, you have got your single update and back propagate. So if you do this, then you will have to wait for huge amount of time, and that is actually the actual gradient descent. But instead of that, we every time do it in terms of batches. So that is why in CNNs, we divide the whole data set into small batches. Here also, we are going to divide it into small batches. And these batches are not going to say that in each batch, probably you may have, this is batch number 1, this is batch number 2, maybe this is batch number 3. Within a batch, probably you may have multiple sentences, or maybe sometimes you have only one sentence, or maybe sometimes you have only one part of a sentence. So it completely depends, and that is why it is back propagation through time. And then it's a truncated back propagation through time. So we will truncate it. If you remember that we do not do it, we divide it into, truncate it into multiple batches, and that is actually, I will show from here to here, let my network only unroll up to this, and maybe this is 10 times. So I show 10 things, let my network unroll for only 10 units, and then back propagate, and then show the next 10 things. Is this okay, Avantika, Anushka?
So what I'm trying to says that if we update the parameters, then the network changes. So is it that
Yes,
at minimum when we are using, let's say if we use just one, the minimum unit is a sentence, or it could be a part of a sentence also?
that's why I said that it is actually like a batch. So within a batch, probably you may have 10 words, maybe 20 words, and these words may be coming from one sentence, maybe coming from multiple sentences. It actually depends upon how much you can unroll. Unrolling is going to take a huge amount of memory as well. So suppose that you have fixed that I'm going to unroll after 10. So which means that after 10 units, what will happen is that all the weights that you have got, your weights got, you have got your delta W's, and delta W's got back propagated, and it keep on back propagating, in the network, and you are going to have these only after 10 time steps. In this 10 time step, it may be that it's coming words are coming from a sentence, maybe coming from two sentences or five sentences. It doesn't matter. It depends upon the amount of memory that you have and how much amount of time that you can spend for your back propagation. Still it is not clear.
Okay.
It may be that probably is it not clear. Anyone can also ask, or if it's not clear to him or her, then you can again ask. I guess that the question was that why, or what's the minimum time quantum? Time quanta can be even after seeing every word you wanted to back propagate. It is just like single instance back propagation. Sometimes you say that no, after 10 units, after seeing 10 units, I'm back propagating. So that is a small batch. Or sometimes you will say, no, I will see the whole corpus and then I wanted to back propagate. And that is actually the full back propagation. That's never been happening. So every time we do batch mode. So truncated back prop, TBTT, truncated back propagation through time. Is this okay to everyone, or anyone is having any other question? Right. So once it is done, we are not going to see this stuff because I assume that you all can understand that then RNN is having certain issues, and using those RNNs exactly similar protocol we have developed GRUs and LSTMs and so on. And we have seen that they can provide us better long-term, short-term dependency. So this is done. And one thing which is called as unrolling, and other thing which is called as look back. So you all understand that what does this look back mean. So here you can see that given this input sequence, I will see one and predict two and then predict three. Then somebody say that no, I want to see one and two and then I predict three. Somebody will say then one, two, and three I will see and then I predict four. So that's actually the look back. Uh, and a roll. What we say that this thing is actually called as a rollback. How much amount of rollback after showing it to a one instance? I guess that there is some doubt. So let me show you another thing that I wanted to. Maybe I have to go here and take another page. Oh, it comes over here. Yes. So in this page, what I'm going to do is that. Yeah, suppose that I'm having let me write something like I'm having instance number one. This is some sentence which is having certain number of words. Then I'm having instance number two. This is another sentence which is having certain number of words. And for this word my class is C1, and for this my class is C2, and for any I, and all these sentences are actually of different lengths, and that's my class is CI. I have a network like this RNN, and it will take and if I write it like x1, x2, x3, x4 and so on, Then it will see x1, then x2, then x3, then x4, and x5, and then at last it is going to tell me the class that has to be C1. And this is which type of network? This is RNN with many to one, because you see many things and then you are going to give me one single output. That is actually a classification that we are doing. Now in this case, now suppose that my RNN is going to be unrolled only after um, five elements. So once I see 5 elements, so I will see x1 to x5, accumulate my gradients, and then after that I will change my weights of my network x6 to x10, and then accumulate my gradients, and then second round update, and assume that in I5 I am having 12 elements. Then first I back propagate for this. Then what is happening? I don't know. So for first these things I will update here. Okay, sorry. So for first 5 I will update. For the next 5 I will update, and then for 2 I will do x11 I will show, x12 I will show, find out the classification, and reset my gates. Because I am done with one set of, one input is being shown, everything is done. I need to, RNN is having a state. The state of this RNN has to be reset. Otherwise what will happen? It will not be able to understand that one instance is done. I have to generate this, need to generate this, and then you find out your losses, and then you can back propagate. So what I have said is that in this, probably you are going to, you was actually being confusing between the fact that one sentence may have, 5 things, then the next 5 things, and then 2 things. This 5 and 2 is being divided in such a way so that my neural network is only unrolling for, or RNN unit is only unrolling for 5 elements. After 5 elements I back propagate, after these 5 elements I back propagate, and after 2 elements I have got a class. Till now I didn't have even got a final class. Once you have got a class, then probably you started to do this type of back propagation at all. So you keep on doing this an analysis, and keep on regressing, back propagating like this. But the other point that I wanted to make is that now we are going towards another uh, area in which we actually wanted to look for is actually why it's not working, I don't know. So we are going to work for sequence to sequence modeling. So what is the sequence to sequence modeling? And for this sequence to sequence modeling, things are going to be handy, helpful, and for this actually transformer is most of the time being used. In fact, RNN is also being used for the same thing. Now let us see this once again, that there is one other model that's actually being called as many to many model. What it is? That I am having a language to language translation, I am having sequence to sequence translation, then I have a recurrent unit, and it's keep on unrolling like this. I am showing x1, I am showing x2, I am showing x3, x4, and x5. And here, instead of generating certain thing, I have got actually a context. I pass this context to the next layer, in which now I started to generate my output. So this is my y1, this is my y2, and this is my y3. So that is why it is, you are having many things over here, and you are generating many things over there. Language translation is one such an example. And if you remember that in our previous lectures, we have also shown that how these type of networks are being made. First, this type of thing can be made, then this type of thing, and this is actually many to one, and this can be seen as one to many, and both of these things when got added, you have got a many to many network. That's actually a sequence to sequence modeling that is going to happen. So now what we are going to do is that to understand how this sequence to sequence modeling is actually being realized, and what are the pros and cons, and then we will move on to transformers. Yes, any questions till now?
Sir, in this many-to-many sequence-to-sequence modeling, why don't we directly give X1 and produce Y1? Why are we first using a many-to-one sequence and then producing a one-to-many sequence?
Yes, so it's always not true that x1 is only related to y1. Suppose that I wanted to write that I am going, and here it is, मैं जाना चाहता हूँ. So every time it may not be the thing that only this thing is being related to this. This is first thing. Secondly, if you want to say that every xi is being related to yi, then it doesn't have, time dependency between the previous things. Who is going to manage this stuff that previous things are also being related? Yeah, that's correct. Is this okay,
Yes,
Pratik? Yeah.
sir.
Because when you are generating something over here, you not only are interested in this, you are interested in all of them, because remember the example of Virat Kohli that I every time used to give, that RNN is actually behaving like Virat Kohli. So it doesn't matter that what he has said in the previous interview. If you ask the same question every time, same question, same x3 is going to give you different answers depending upon the context. So that's why you keep on remembering the things, and only this thing is not going to be helpful. Is this okay?
Yes, sir.
Yes. Yes, so this was the sequence to sequence modeling and many to many. This is the first time we are going to see sequence to sequence modeling, most of the time being very very relevant when we are talking about when we are talking about, if I say, um, language to language translations. So let us see, and I'm going to use a very specific blog for this, and directly from there I'm going to teach. He has written very well, this guy Jay LMR, and he has worked very hard to make all these things visually possible. So that's why I'm using, and with this visual blog, probably very easily you all can understand. Let us see. So let us understand the first thing, and you all can see that I'm not sure that I will be able to use my uh, this cursor over this. So probably if I need to write, I will use another place. But try to see that what is happening over here. You can see that x1, y1, sorry, these green things, they are actually going in to a sequence to sequence modeling. These circles are going in and triangles are going out. So this is actually sequence to sequence modeling, and you can see that first all triangle circles go in, and understand that the whole sequence context, and depending upon that it is started to give me the triangles one by one. Now let us see this thing in the case of this natural language processing or sequence to sequence modeling when we are training a language to language model. This language to language model is saying that first I will see something written in French, something which is being written in the left side. Then this moves into the sequence to sequence modeling, and then you can see that I am a student. Then you can see that it's written that I am a student. So here you see that 3 words are going and 4 words are coming out. Sometimes n words are going and m words are coming out, and but it actually depends upon that how these things are related between. I mean, how these things are related, and the way in which things are related, it's actually been working in that way. So I assume that this is also clear to everyone. In between, if anyone is having any doubt, you can please ask. This is directly from the blog, so anyways I have given the credit to the guy from whose blog I'm going to use. Now let us see that slightly moving inside this, that what is happening into this black box of sequence to sequence modeling. And now you can see that there is an encoder and a decoder. So as I have said that many to one can be seen as one encoder, and one to many can be seen as another a decoder. So encoder is looking this all circles, understanding that what you wanted to do, what is happening in this circle business. Maybe some language is there. What is happening in that language? What is the semantic of that language? What is the syntax of that language? Encoding everything into some useful information, and I'm going to pass that information to the decoder, and triangles are going to be made out of that. Now let us see that how this thing is being translated into uh, the same thing is going to happen in the case of language translation. G sends to the decoder is generating one by one. So only given that context, you see that only given that small amount of context, whatever it's being there, decoder is generating the sequence, which is the second sequence that need to be generated. So one should have to understand that context need to be properly modeled. Context need to be not only properly modeled but have to be properly learned, so that this context is the only thing which is being fed to the decoder. Decoder has actually not even seen what's being the input to the encoder. It only have seen the context, and using this context, decoder is going to generate all that sequence number to one by one. So this context can now be seen as you can see a vector like this, and this vector having 4 values. So we have chosen that context need to be four dimension. Maybe it's an example. Usually it is 300 to 400 dimensional vector. And then you can see that this color coding is actually telling that the value which is high, you are saying that its value is so it's having actually a bright color, and the small values are showing less color. So which essentially mean that context is being encoded as a vector with a very specific type of values for each and every dimension which is being there in the context, and that is going to be helpful when you are going to decode the output sequence using only this context. So as it's being written that several places, it's like 256, 512 and 1024 type of context. So before going to talk about anything else, one should have to understand that these G and whatever the French sentence it's being written, G sends to Dante, and then the output is going to be I am a student. All these things are actually words, and network is not going to see these things in the plain form of these words. So how our network can somehow understand that what it is looking their sentences? So there has to be a proper, so the network cannot see these sentences. It can only see um, vectors. It can only see numbers and vectors. So there has to be a way by which we can convert a given word, whatever the word that we have, into a vector, because our encoder is going to see word by word our sentences, and decoder is to generate word by word the output. So the way in which this context is actually being converted into a vector, these words also have to be somehow being converted into some word embeddings. So you can see that RNN is actually going to take these word embeddings, and these word embeddings has to have the meanings and the semantic information related to these words, like king. So if I have an embedding of king, and an embedding of man, and an embedding of woman, and if I take king's embedding minus the man embedding and add the woman's embedding, it has to be somehow coming on to be very similar to the embedding of the queen. So now you can see that word embedding is not readily available for us. We require certain an embedding which you can say that capturing the semantic meaning of that word. So there is a king, so there is a semantic meaning related to a king, because king and queen, they can be close to each other, man and woman can be close to each other, but man and king, they're also close, and woman and queen, they're also close. So who is going to, somehow figure out that how to come up with the best possible these word embedding? So word to work and glove, glove, these are two different types of available word embeddings for which networks are directly being available, and these networks directly take word embeddings from, directly take the word from you, pass it to the network, and it's going to give you the corresponding embedding. How to get that? So that is one thing that we are going to see. Till now, is there any question that you wanted to ask? It is just being shown over here that these are the inputs in which you are having 1, 2, and 3 things being written, 3 words. And for all these 3 words, I am having a 4-dimensional word to vec type of embedding. And these are being, they can be computed using pre-trained embeddings. Any question till now? Okay. Yes, so word to vec embedding we are going to do. So word to vec embedding, and again, these things I am taking from YouTube lecture by Mensuk Hyo from YouTube. Neural networks can see as the input data that's being encoded, and in the form of vectors. It can only see vectors. You have got a text, whatever. If you want to show it to a network, it has to be encoded in such a way so that my network can see. Now, suppose if I am going to eat, I am going to work, I need to find out what are the unique words which are being there. So this is going to be my big, or the whole corpus, or the data over which I'm going to work on. I'm having 2 sentences. You may have 50 sentences, 1,000 sentences, or 50,000 sentences. Out of that, you need to come up with whatever the unique words that you have. I am going to eat, or whatever the work, and so on. And for each and every word, if you give a decimal encoding, and then you can have 0, 1, 2, 3, 4, and can I use this type of decimal encoding? And then you will say that no, we usually use the one hot encoding. Now, if I say that these are the one hot encodings for all these guys, we are also okay with this. Now, can you tell me that why we are not using these one hot encoding? And we wanted to train another network that is going to be talking about a word to vec type of network. Can I ask this to, can I ask it to Anurag Pandey? Anurag, can you listen? Okay, I assume that he is not here. Hey, Lokendra, can you listen?
yes sir, अनुराग बोला था.
Anurag, yes.
सर उसका साइज बहुत बड़ा हो जाएगा सर.
इसका साइज बहुत बड़ा हो सकता है, but that is a secondary answer. This is also one answer, because unique words are going to be too many, and if there are 10,000 or 50,000 unique words, then your one hot encoding is going to be 50,000 dimensional, which is infeasible. Yes, but any other reason, any other very specific reason why you do not require one hot encoding in such cases?
कंपेयर करने में भी दिक्कत होगी सर.
क्या दिक्कत होगी
सर? क्योंकि साइज बड़ा होता जाएगा तो उस केस में सर कंपेयर करने में प्रॉब्लम नहीं होगी सर.
So anyways, that is one issue. What is the other issue? Okay, let us ask. Yes, say.
Sir, I guess similarity, say there are 2 words which are similar to each other.
Yeah.
These kinds of things will not come in one-hot encoding, since all of the vectors are orthogonal to each other. So every word is treated separately. You cannot put the similarity kind of a thing.
Yes, that is the answer. And the reason is that if you remember why we have used one hot encoding, and if you go to my previous lectures in which we have talked about the reason between one hot encoding and decimal encoding, was that in one hot encoding there is no ordinal relationship. No one is bigger or smaller than anyone. Everyone is having its own orthogonal space. So each and every one hot encoding distance between two one hot encoding is actually root 2. So because of that, everything is at a same distance to each other. And this is a thing that we precisely do not want, because then these words will not be having any relationship between them. And if they are not having any relationship between them, no semantic information available, then how can we predict after seeing certain things, how can we predict the previous things? So one hot encoding is definitely going to be a very, long embeddings. But the main reason also is that we do not require such type of matching, embeddings, because I am going to eat and work, all of them are actually having orthogonal embeddings, and we do not require such type of encoding. Now let us see that we require that there is king, there is man, there is queen, there is woman, and suppose that king is having 1,2 embedding, man is having 1,3, queen is having 5,1, and woman is having 5,3. So this is my king's embedding 1,2, man's embedding 1,3. This is like my queen's embedding 5, 1, and maybe one woman's embedding, which is actually 5,3. So now you can see that they are actually near. This is also near to this, but it's actually far from this. But this guy is near to this, and this is also near to this. So some type of embedding which is having a notion that that king and queen, they are related, man and woman, they are related. The king and queen are related in such a way, the way in which man and woman are related. Then king is actually a man, queen is actually a woman. So if that is if your embedding actually understand this thing, then king minus man plus woman is going to give you something which is going to be queen. So similarity has to be somehow embedded in my encoding. Then if I give you two embeddings like this, then you can say that okay, this king is actually far from woman, but because of uh, certain things, king and queen, they are close to each other. Yes. Any question do you want to ask?
सर इसको दोबारा एक्सप्लेन कर सकते हैं?
This is only just saying that king. This is saying that king and queen, they are related, man and woman, they are related, and the way in which king and queen are related, man and woman are also related in the same way. So yes,
इसमें डाउट ये हो रहा है, ये क्वीन 5,1 है या 5,2 होगी सर?
maybe numbers may be slightly different. You can see over here.
Okay.
I just want to give you an example in which it is saying that king and, but king and woman is different, far. So if you somehow get the relationship between king and the embedding for king and subtract it from man and then add a woman, it has to somehow come up to q. It's some type of vector addition which is going to happen in terms of similarity. So if I give you a king embedding and if I give you a queen embedding, that the cosine similarity has to be less. And if I give you a king and a woman, then the cosine similarity may be high. So we need to train such a network which is going to give us such type of semantically meaningful embeddings, right? So can we do it? It can be done using word to vec. And how we are going to do that? Let us see two sentences, sentence number 1 and sentence number 2. These are my two sentences. And as I have said that most of the common stop words like is, am, are, the, that, these should not be used. Or if you are using them, then they are most of the time being treated in a different way. And nouns and verbs and adjectives, they are being treated in a different way. So you see that the Virat, batsman and good, and here you are having Virat, captain and India. So these things are several times being seen in a sentence, and you understand that if I talk about Virat, then I'm going to talk about, say, some batsman, or I'm going to talk about captain, or I'm going to talk about India, or I'm going to talk about good. If I'm going to talk about captain, then it's going to be somehow related to India. It can be related to Captain Virat as well. If I talk about batsman, then it's also going to be related to Virat in certain ways. It may also be related to Sachin. It may also be related to Sehwag and all, but it's also going to be related to Virat. So these word to work embeddings are actually being trained using a skipgram approach. A skipgram is that it's just, we used to say that what is n-gram. So n-gram is that if I take a big sentence and see only n words out of that and say that this is my context. Context means that a contiguous text, into which I am somehow looking to figure out. So if you are related to someone, then you have to be in its context. So if it is, a context like this and a word is here, then and there is another word, so they are having a relationship because they are within a context. So I take a word and find out its context like this. And whatever, so this is my word, all the words which are here, they are being related to this word, and they are constituting a context. And that is why if I say n-gram approach, and if the value of n is equal to 5, then it's going to be a 5 words in my context, taking the center word, then 2 words previous and 2 words forward. So this is my center word, and this is my context over which I am going to work on. And let us see that if I work on WS, my context size or the window size is actually equal to 1, or is it equal to 2. For both of these, I am just showing that how we are going to get my network trained, and how we are getting the ground truth. That's going to be, I'm having words and I'm having neighbors. So Virat, batsman, good. Virat, captain in India. So Virat and batsman, if my window size is 1, so Virat and batsman. Then batsman and good, batsman and Virat. So you can see that batsman Virat, batsman good. Then you can say that good, so you can have only the batsman for this. So good and batsman. This is going to be that relationship, that if I say Virat, then it is also having a relationship with batsman. If I say batsman, it is having relationship with Virat, having relationship with good. If I show you good, it is having relationship with batsman, and so on, and do it for the whole data set. Similarly, if I take WS equal to 2 size window, then Virat is not only related to batsman, Virat is also related to good. So this word size is actually going to say that how much context that I am looking for, and how much amount of big or the long-term dependency which is being there. Because Virat is here, and Virat is actually being, somehow related to good when my window size is getting bigger and bigger. So if I take a very big window size, then probably several things become related to each other. If I take a very small window size, not everything is related, or too many things are related. Basically, in this way, what you are going to have is that we are going to have certain words over here and the corresponding things to which it's actually related. So I'm going to have a set of pair. I'm having X that I show to my network, and I will be having Y that I want my network to predict. I wanted my network to really understand the relationship, that there is a relationship that batsman is also related to Virat. It's also related to good. Good is also related to batsman. Virat is related to captain. So if I show my network this Virat, it is somehow have to say that captain. If I show captain, it has to say Virat. If I show captain, it has to say India. So I need to train a network which will take things from here and convert it into here. Now, that is going to be understanding the semantic relationship which is actually between these pairs. And how we can do this? It can be done using, so I will take the words, or say X as I've shown, and the neighboring words are going to be Y that we wanted my network to predict. I take this word, show it to my network. Before showing, I convert it into a one-hot encoding, and then input it to my network. And for inputting once I input it to my network, you are going to get the neural network, and then you get your output. So how you are going to get this output? So this output is your neural network will take this word, and you have got your output, and the neighborhood word is also going to be fed into your network. Sorry, your neighborhood word is actually having a one hot encoding. So whatever you are getting as an output, you need to check that how far it is from this neighborhood embedding. And you are training your network in this way that Virat will go in, and as an output certain things that are being, batsman or good or captain or India, because these things are related to Virat, they have to be predicted. So I will take Virat and first input this. So this is my input, this is my output, this is my in between. So this is actually a feed forward, simple feed forward neural network, which will take things going in and things going out. This is my first layer, linear layer. These are my set of weights which are being applied over here. These are my set of weights which are being applied over here. I is the input, O is the output. Virat will go in, batsman has to come out, then again Virat will go in, good need to come out, then again Virat may go in, and captain should have to be coming out, and again Virat go in, and India need to be coming out. So in this way, I am going to send all of them one by one into my network, and let this network understand what is the hidden representation. And from this simple single hidden representation, it is actually generating this. What this hidden representation actually mean? Now let us see that this I is my input, which is going to be multiplied with MA, and assuming that my input is actually only 5 dimensions. So my input dimension is 5 cross 1. MA is going to be 2 cross 5. And when I multiply, you are going to get a hidden representation 2 cross 1. And this hidden representation is actually multiplying between, multiplied by this MB, my second network or second layer, the weights. And that's going to be MB, that's 5 cross 2. This is 2 cross 1. And you are going to get a 5 cross 1 as an output. That's my output. So I will give 5-dimensional thing. I'm getting 5-dimensional output. And it's almost like a type of autoencoder, in which I am showing this, I am getting this, I am training it so as to get something over here, and what you are getting is actually the thing that is being in which we are interested. Why? Because MA is 2 cross 5. So I just have drawn this matrix for you. That's a 2 rows and 5 columns, and this is 5 cross 1. This is 1, 2, 3, 4, and 5. Out of that, and not only this, this is actually a one hot encoded. So only one place it is high. So suppose that it is high at one place, and which is this. Its ith element is high, and suppose that the first element is high. You are only going to get this thing as an output. When your second element is high, you are only going to get this thing. If your ith element is high, you are only going to get the ith column of this MA. When you multiply this and when you got this hidden representation. So actually what is happening is that given this matrix MA, when you multiply with your I, you are going to get an output H, and this output is actually nothing but a 2-dimensional representation of this, which can describe my input in the best possible way, so that it can fulfill all of its relationships. So this is actually going to be the hidden representation of my world. So MA is nothing but actually a matrix, and this matrix, when got multiplied with 0, 1 or any binary or any one hot encoded vector, it will just select certain columns. So if it is a fifth element, the fifth element's output or the fifth element's vector representation is actually this one. So in this way, actually this one hot encoding is working. This network is actually being trained. Multiple other optimizations are also being done so as to make this representation as robust and best possible. And once this network is trained, you are not interested in this. You just take this much, this part, take whatever the word that you want, network, pass it to your network, find out the hidden representation, and that is the embedding for that word. So that is actually word to work for you. Let's take few questions if you have. Word to work and embedding is this. Yes. So this is actually word to work embedding, in which we are saying that any input, you can say, can actually be converted into words. Sorry, converted into network. Is this okay to everyone? Is there anyone who wanted to ask any question?
Sir,
Yes,
sir. So, could
please
you
ask.
go back to the notes? Right. So, sir, over here you mentioned that say Virat will go in and batsman will come out. So, is this
Yes.
random? Randomly batsman may come out or randomly good may come out. So, how do these come out?
So they're not coming out. It is just that you take this network, it will go in. So you, right now, the pair over which you are training is Virat, comma batsman.
Right.
So first Virat will go and batsman had to come out. If it is not coming out, then that is going to be fed as a, taken as a loss. And you do cross entropy and soft max and cross entropy, and find out the loss, and then back propagate. And then you again show so now the second pair is going to be Virat comma good. Then the third pair can be Virat comma captain, then Virat comma India, and keep on doing for good amount of time. You
So,
have to do it for all of them. Yes.
So learning rule may be different because say once I give Virat and batsman this pair, and then I
Yes.
change the pair Virat and good, so the weights may get misleaded some kind of.
Yes. So it's going to happen, and yes, um, one should have to understand it's not a recurrent neural network, so it's not going to remember that Virat and batsman. So it has to that at finally when your network is converging, it is assuming that for Virat, all these things have to give small distances. Otherwise, I am going to get more and more loss.
Okay, sir.
Okay. So so in this way, what's being done is that we have got the word embedding. So once we have got this word embedding, let us see this how this recurrent neural network is actually working. And this recurrent neural network actually works. So I assume that all of us can now understand that how this thing is working. I'm not able to use my this thing screen, so I can show it from here. That right now I'm concentrating over here. That time step 1, you are having hidden states, you are having input vector, and given hidden state, this thing given hidden states and input vector, what we are going to do is that in the right hand side we have got the RNN units. We all know that input is going in, this input is actually going in, and hidden state, both of them are being used so as to get the hidden state 1, that is the hidden state 0, and input 1 is going to give you the hidden state 1, and using that you are computing the output. So this is the whole thing. So you have got two things. What you have generated the hidden state as well as the output vector, hidden state and the output vector. Then let us see it in a slightly different way, in which word instead of those values, let us show that words are going in. Anyways, words are not going, but words in the form of vector they are going, and these word vectors are going to my encoder like this. Step 1, step 2, step 3, step 4, And now you see that in step 4, so what is happened till now is that you have shown your input one by one. And once you have shown your input one by one, let us say it again. Once you show your input one by one, first input go in, you have got a hidden state, second in, then hidden state and the input, and the hidden state and the input, you have got the final output, and the output is nothing but a hidden state. And then all the inputs are being, seen by the decoder. Decoder has only seen the context, or you can say that the hidden state, the last hidden state. Now you see that the last hidden state is this. Now this is only going inside my decoder. Decoder has to see this and has to generate I am a student at 4 time steps. After seeing, so 3 time steps you are looking the input, and then 4 time steps you are generating the output. Is this clear to everyone, or you need to ask anything over here? It's very straightforward. I assume that this is clear to everyone. Now let us see it. That is why I liked it, because he has shown so many, visually shown all this stuff. So I thought that to present from here. Now you see that RNN, and this is another unrolling of an RNN. So the same RNN got unrolled, and one by one you can see that it's going one to encoder, and then decoder is decoding all of these things one by one. Let us see it once more. That first this will go in, then the second word will go in, and then the third word is going in, and encoder is nothing but unrolling itself. So it's got unrolled, you have got hidden state 1, then it's got unrolled, then you've got the second state, then you got again unrolling, and you've got the third hidden state going into my decoder. Now you are seeing that decoder has generated I, then the second, and every time remember one thing which is not being shown here, being written, but it's not being shown, that decoder has actually got as an input the context or the hidden state from my encoder. But decoder is also having its own hidden state. Every time decoder is also having its own hidden state, which is being going. So along with its own hidden state, as well as the encoder's last hidden state, using both of those things, decoder is actually generating I am a student. Let us see it once more. They all are going one by one. We are getting the hidden states. Now one should have to understand that last hidden state has to remember most of the things which are being there in my my words or the sentences, and decoder is because only looking the final thing, and from that it is generating the whole sentence. So the whole essence of the sentence somehow to be embedded, encoded by encoder in its final hidden state, and decoder is taking that, and understand that the decoder has taken that only one single final hidden states context, and it is using that context to generate I. Then the next time step generated am, using the same context. Using the same context, it is generating multiple different things. How? Because its own decoder is trained in such a way so that at different time steps it has to generate different things given the same type of hidden state representation. So this is actually the plain type of neural network which is happening. Then later what happened is that now you understand that when I show you, so now you can ask that, sir, when I show G, yes, or studente, then why? So that all the three things that I have shown in French, they are being encoded and being shown as a single hidden state to the decoder, and it is trying to somehow extract the student out of it at the 7th time step. At the 4th time step, it is trying to extract I out of it. In the 5th time step, it is trying to extract M out of it. In the 7th or the 6th time step, A, and in the 7th time step, probably student. So it's trying to extract multiple words out of it at different time steps. Then somebody will say that, sir, all of them are actually having 3 different states. but you are using only the final, and network has to place all the information into that final state. Is it not a better way to first of all pass all the previous states? One thing. And secondly, while predicting student, it can give more weightage. Somehow understand that I have to give more weightage to the hidden state that I have got after my third encoder, because one third encoder has seen student, studente, that is in French. If I give more weightage to that hidden state, probably I may get slightly better results. So let us understand this. That's actually been converted into the form that's being called as the paying attention. So we also not only, you know, predict, can I also learn an attention? So that's also being written at that at 7th time step, when you are going to, when you have predicted I am a, and now you are going to predict student, and at that point of time, network has to give more and more weightage to the embedding or to the hidden state uh, in which my encoder was when I was looking the studente in French. And if I can somehow learn that and give more and more weightage to the things that I am predicting, that I'm about to predict, that is actually the attention. So attention, first of all, say that now you can see that this is attention, in which again you are getting 3 hidden states, and 3 hidden states, not only one but all of them are going to be simultaneously being given to all of my attention decoder. So these decoders are not single decoder or simple decoder, they are the attention decoders. They are going to use all of my hidden state 1, 2 and 3. They all are being fixed, not being changing, and shown to my attention decoder. Attention decoder is going to use all the 3 hidden states. First attention decoder is not only going to predict I, but also is going to learn how much amount of weight should I give to my first hidden representation, how much amount of weight should I give to my second hidden representation, and how much amount of weight I should have to give to my third hidden representation, and then merge and get a single hidden representation. Use that hidden representation along with the my own hidden representation, and then predict I. So now you can see that instead of one single hidden representation, network at every time step is learning that for I have to give, when I am predicting I, or the 5th time step, I have to give more weightage to hidden state 1. When I'm going to predict M, time step 6, I have to give more weightage to hidden representation 2, and then more hidden representation to hidden state 3. Sometimes I have to give more weight to multiple hidden representations, and that is soon that you are going to see. So actually, let me show that how this computation is actually working. Yes.
Sir, can you please go back to the previous page?
Ashma, if you wait once, I am sure that you will be able to understand this because in this video, it's actually been shown in this animation. So I am again coming back to you, Ashma.
Okay, sir.
Yeah, so you can see that attention at any step 4. Step number 4 is the step in all 3 hidden previous states. They are being shown that prepare your inputs. So you have got hidden state 1, 2, 3 that you have got, and your decoder is also having its own hidden state. That is step number 4. Decoder itself is having its own hidden state, and then somehow you have a network which is being learning that how much amount of weight should I give to H1, say 13. H2 I wanted to give 9, and H3 I wanted to give 9. And over that I apply some softmax, which is going to tell you that hidden state 1 is getting more weight, others are getting less weight. Why? Because time step 1 is there, and first one has to have more weight than the others. It somehow learn this thing. And then I multiply 0.96 with H1, 0.02 with H2 and 0.02 with H3. Add all of them, and the fifth step, I add all of them. So I have got a context vector. Now this is the context vector. Previously, what was your context vector? That was only H3. Now your context vector is H1 plus H2 plus H3, but not the basic addition or the averaging. This is a learned, attention-based learning is happening. Weights being learned not only for one time step, but for every time before you are going to predict something, you try to learn as a network attention decoder tries to learn how much amount of weight one should have to give to any HI, and then I give that weights, add it up, and have got a context vector. Now this context vector and along with this purple thing, decoder hidden state at time step 4, both of these things are concatenated and being used for prediction. Then we will see how it's been done. Now Ashima, you can ask.
Sir, now you said that the first decoder will get the 3 hidden representations from the encoder.
Yes.
Okay, so then the second decoder will get those 3 plus the one generated by the previous decoder.
See Ashima, let me clear it down that these are not different decoders. They are the same decoders. This is just only the unrolling. This is first thing. Second thing is that this decoder, where it is, yeah. So here it is getting 3 things. All of them are actually getting these 3 things. Along with that, and they are fixed. They are not changing. These orange things are fixed and being given to attention decoder. And all of them are actually the same attention decoder, just the unrolling of same RNN. But what is being changing is its own hidden state at every time step. That's why it's being shown in purple color over here. In purple color over here, it's being shown. हाँ 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 मेरी क्लास चल रही है मेरी. Okay. You talk to Sonu. I am teaching. Correct. Ashima, do you understand?
Sir, but we also get the hidden state from the previous time step.
Yes, so hidden state of the previous time step is actually in purple color, right? That is for every, that is for the decoder. And at every time step that is changing.
Oh, okay. Okay,
every time step that is changing. But this purple, this orange things are fixed. They are actually the encoder RNN hidden states.
Okay, sir.
Is this okay to everyone?
Yes, sir.
Yes. So now how this whole computation is being done, let us see once. And that is very, very simple. Now if we all understand, we are about to finish. So now you can see that let it be finished. Let me show this video once. Hidden state all. Now this is actually computing the attention. So in this dotted block, you can see the attention is being there, and once attention is being learned, so now you can see that attention number 4. So first you have got H initialization, then you have got the end vector, because end vector is always the first vector that your decoder is going to see, and decoder see the hidden state and the end vector and generate your H4, the hidden state. And this H4 is not being used alone, but has to be used by the context, concatenated with the constant context. Previously, that context was only H3. Now, instead of that H3, I have got H1, H2, H3. I merge all of them, and how I am merging them? I am learning this, pink color weights for each and every H1, H2, and H3. And once using these weights, when I do the weighing, I will get this blue color output, and this output is nothing but the actual context that now we are going to use. That is a learned attention, or learned attention is actually, one can say that this pink thing. Using that learned attention, I have got the aggregated context, and that C4, the context that I have got, I concatenated with C4 and H4. Once you have got this concatenated C4 and H4, that is going into the fully connected network, so as to give you the final output that has to be equal to I. Once you have got that, now this I will go where I is going. Now you can see that I has to go into my unrolled version of the same RNN. Now you can see that given the H4 and the previous output, I have got H4. Given this H5, given this H5, I learn again the attention, and attention is going to be learned over H1, H2 and H3. So again you see that H1, H2, I learn this attention, and this attention say that I have to give more weight now to the second column. I learn it in that way. Then I combine them. I have got C5, then I concat them and show it to my fully connected network, which is going to give me the final output. So for every time step, my recurrent network is not only changing and learning its own hidden representation, but also learning attention in such a way so that how much amount of weightage one should be giving to H1, H2 and H3 so as to get the best possible context. So in this way, sequence learning with attention is going to happen. Again, he has shown, and now Anurag was asking initially something. So let us see that thing. That suppose that Jesus and Siddhante is being written in my left, and on the top it's being written I am a student. It has been shown that when which state has got more weight. So state 1, state 2 and state 3, we all know that state 1 is corresponding to J, state 2 is being corresponded to Swiss, and state 3 is being corresponding to Studante, and which is going to get the, so when I am going to predict I, first hidden state has got more weight. When I'm predicting M, the second has got more weight. When I'm predicting A, you can see that the second and third has got, you know, weight. And when I'm predicting a student, then the last hidden or the hidden state 3 has got more and more weight. It has to be learned, and it's being seen that these weights are being learned in such a way so that network can better focus and give more and more attention to the relevant hidden states while predicting the things. Yes, I'm done with this, and this is again being shown in the same way, that left side is being written with the French words and the top is being written in the English words. And you can see that not every time only one hidden state or the one word has got more attention. Sometimes a pair of words have got more attention. Sometimes a group of words got more attention. So in this way, network started to sequence to sequence learning actually started to perform well, and started to give more and more attention to the hidden states, the relevant hidden states. Yes, I am done. If there is anyone who want to ask any question, so you can ask. Several things are being written here, so we can share this link as well. So from here also you can read it again. Thank you. Any other question? In the next lecture, we are going to start from this base. In the next lecture, we are going to start transformers. Okay, no question then. Thank you very much.
Thank you, sir.